Hello, my name is Gabriel Perry. I am a second year master's student at Brigham Young University in the computer science department under Sean Warnick, Dr. Sean Warnick, my advisor. I am graduating next week. This is a project that I am completing for Computer Science 677, a course here at BYU. My final project for this course titled Bayesian ARX Identification for Robust Control and Attack Resilient Analysis. This course, Bayesian Methods in Computer Science, requires us to learn about Bayesian statistics, especially with these parameterized models and machine learning models that are becoming so important nowadays. And we have learned throughout the semester how to apply Bayesian statistics to the parameters in these models. So my project, the core message is that Bayesian methods preserve the set of controlled plants. So these are systems. And these systems, when we identify them from input-output data, they can hide uncertainty depending on if the data is sparse or if it under constrains the system we're trying to identify. But they can produce point estimates of these systems, a single set of parameters that is the best fit for that data. And I wanted to introduce the Bayesian framework into the world of system identification so that when we ask questions from robust control theory on these systems, such as stability or the margins of stability, how robust is the system, we can do so not just on the best fit model, but also probabilistically on the set of all plausible models based on the data that we used to identify the system. Motivation for this comes from research in our lab and IDEA labs here in the computer science department, that when working with small utilities, we want to help them identify vulnerabilities in their systems. So think small town power grids that just supply the one town or maybe the county. They don't have the budget or the staffing oftentimes to produce high fidelity models that your larger utilities might just have available. These are systems which might be running on Windows XP. The topology of the system, the components of the system might have been logged in 20-year-old software 20 years ago. And all they really have is day-to-day operational data that they use for billing. And that's just the data that they have available. But we would want to be able to use that data anyways, as it is, in order to perform an analysis of their system to identify vulnerabilities. Now, in order to do that with the kind of data that they have, we would need explicit guarantees on the uncertainty in that analysis. And that's where the Bayesian framework comes in. Because instead of providing one point estimate of the system, the Bayesian approach allows us to propagate uncertainty inherent in the data into uncertainty in the parameters, and ultimately to retain that uncertainty in the output data as well, and in the other analyses that we would wish to perform, as we will see through this presentation. So first, what are we talking about when we say system? So these are discrete time, single input, single output systems identified using autoregressive exogenous inputs. So this ARX way of identifying the model is to use the autoregressive. So this is the kind of like the state. So it regresses on its own state. But we aren't going to consider the internal state because we don't have access to this. We are just considering the past observed states, Y, as well as the exogenous inputs, the U's. And we are going to assume that the system is linear. So we see here that the output Y at time t is going to be equal to this inner product between the past observed outputs and inputs phi, as well as the model parameters that we are trying to identify theta, plus the noise term, which handles just real world noise. Whenever you take a measurement, it is noisy, so it is helpful to explicitly identify that noise in order to make the identification more robust to it. And this parameter theta is the thing that we are trying to identify using the input-output data. And we are actually going to use least squares and the projection theorem in order to do that. This is standard linear controls system identification. And we assume that the system is linear at least near the regime that we are going to be identifying, although there are other methods if the system has to be nonlinear. So with that in mind, we are going to identify what we mean by the Bayesian side of, or the Bayesian contribution of this project. We are going to assume that these parameters, these model parameters theta, are not single numbers that we are trying to identify, but rather that they are themselves distributions. They are random variables. Here we are going to specify the priors on, or the prior beliefs of the distribution of those parameters. And we're just going to use a normal distribution for simplicity. So we assume that the parameters theta are normally distributed with a mean, this mu naught vector, and with a covariance between those parameters of sigma naught. We are going to assume an isotropic prior, meaning that this covariance matrix is going to be diagonal, and all the covariances are going to be the same, this alpha squared parameter in the last bullet point. And that just basically means that we are going to say, a priori, we believe that the parameters in the learned model will be approximately the same size, approximately the same spread around their prior mean, mu naught. And this is going to end up being a good assumption for the example systems that we're going to use today, but it might not be a good assumption for a general cyberphysical system. And of course, if the prior on the parameters is normally distributed, the prior on the outputs is also going to be normally distributed. And we're going to get those according to the equation that we saw on the previous slide, with a mean specified by the parameters and the previous outputs and inputs, and with the covariance specified by that noise term. The second thing that makes this Bayesian is updating this prior with the data. So when we see data, we update our prior by multiplying it by a likelihood that we received that data given the parameter, and then again multiplied by the probability that that parameter was the parameterization of our model. And this produces the posterior, an unnormalized posterior distribution, which we can normalize via various methods in Bayesian statistics. The probability that this parameterization of the model is correct given the data that we observed. And if we take the log probability, then we see two terms. The first term, the y minus capital phi theta term, is going to represent the loss function based on the data that we have observed, the data y and phi. And then the second term with that sigma inverse and the mu's, that is going to represent the normalization term in our loss based on the prior beliefs that we brought into the system identification problem. Once we have the posterior distribution, we can begin sampling from that distribution to run our model, to make predictions that our model would state that the system is going to behave in a certain way. And this distribution is going to be sampled from this normal, which is basically the same as the prior, but it has been updated with the data. That's why the mu n and the sigma n feature here, as well as the other terms from the data and the previous inputs that we have observed, because this is a dynamical system. So the controls interpretation here is that a predictive interval is an early warning that polls, margins, and closed loop performance computed from one nominal plant may be fragile. So this is a statement based on analysis which is performed using this system, which at this point, the system is probabilistic, and this is your next x equals f of x term that you would typically see in control theory and in systems. But we have modeled it as this Bayesian function, this normal function based on our data. And this is actually going to be the object that we use to perform our standard robust control analysis. So here we have an example of what happens when we under-constrain the parameters in that system. So we have fewer data points than we have parameters we wish to identify. The red small data, so under-constrained case, has a larger uncertainty, which we would expect when we have not enough data to fully identify the parameters in the system. And the blue band is tighter. That confidence interval is tighter because we have sufficient data to identify the actual intrinsic noise in the process, that original single sigma squared, lowercase sigma squared Gaussian from the nominal model, whereas the red band is wider than that. It also includes uncertainty due to a lack of data. Here's another case. So the Nyquist rate is the fastest rate required or the slowest rate required in order to resolve high frequency data. Basically, if you don't sample fast enough, you aren't going to be able to see things that happen fast in your system. So here we have the blue system trajectory, and these are not the nominal plant, these are the trajectories from the learned models after we have performed system identification using our Bayesian method. The blue curve was learned using samples that satisfy the Nyquist rate, so we are able to resolve the high frequency dynamics. The red curve is a system which has been identified using data which has been sampled below the Nyquist rate. So this data was not sampled frequent enough in order to identify those fast dynamics. And you can see that the blue system is a lot more confident about its predictions, and the red system has had to compensate for its lack of confidence by widening its confidence interval because it can't tell the difference between dynamics and noise due to it not meeting the Nyquist rate. Here is another plot with the poles of the system. This is a discrete time system. So stability is equivalent to the poles being strictly inside of this unit disk. And we see that the system that we have attempted to identify seems to have two poles, one slightly negative and one slightly positive. And the reason that these points are blurred out is because of the posterior distribution of our learned system. These poles are slightly different for the slightly different parameterizations. And stability is actually probabilistic based on our confidence that the poles are within that unit circle. Now, for this particular system, we see that those point clouds are actually pretty confidently inside of the unit disk. So we are fairly confident that this system is stable, the system that we have identified from data. But if there were some of these points outside, then we would be able to say, well, probabilistically, this percent of the points were outside of the circle. So there's this percent probability that the system might actually be unstable. Here is something akin to a Bode plot. So this shows the magnitude of the gains based on the radians of the impulse. So this median curve is what you would typically see as a Bode plot. And the bands represent the posterior probability of that um, curve being in a particular place. So we see that we have high confidence there, sort of where the plot attains its minimum, so it's slightly to the right of its minimum. And we have a lower confidence closer to the static, the zero frequency constant terms. And we have sort of this constant band of uncertainty as we go out to infinity with the frequencies. And uh, the types of analysis that you would perform with a Bodhi plot, you can perform with this plot, and that confidence interval tells you, oh, well, whatever analysis you're going to perform with this Bodhi plot, expect your plot to sort of be within this band. And a similar thing happens here with the Nyquist plot, which is another useful plot for single input, single output systems. So the Nyquist plot also tells us about stability, particularly the number of times. So it's going to plot out the magnitude of the gain similar to the Bodhi plot, but it's going to be in a polar format as we walk along the imaginary axis of the frequency response of the system. A lot of technical details. Basically, if this curve wraps around -1, it better wrap around a particular number of times. I believe it's equal to the number of poles in the system, or else the system will be unstable. And if it satisfies that number of wrapping around the point -1, this red dot on the left diagram, then we can characterize the robustness margin, or how close it is to being unstable, based on how close the curve comes to being on the other side of that point of not wrapping around the proper number of times. And here on the left, we see the posterior median curve, this orange curve going around that point -1. And we also see our point cloud has now become this curve cloud. So this is the posterior distribution of Nyquist plots. And we see that some of them come pretty close to that -1 point. And in particular, there's a max near critical probability. So that's probability of 0.01% of the posterior is close enough to that point -1 that we are a little bit concerned about the robustness margins of the system. So we could go to the person that we're reporting to and say, hey, there is a 1% chance that your system that we identified might be unstable because that Nyquist plot might go around -1 the incorrect number of times with 1% probability. So that's the kind of analysis that we would be able to perform using the Bayesian model of our system that we would not be able to perform if we just had sort of the 1 point estimate, the mean or the median here in orange system. And here are trajectory evolutions, another thing which are very useful. I mean, we want to run our system. We want to actually make predictions using the system that we identified. So this is the 1 step ahead, which means that we're going to, well, it's actually going to be both. This plot has both. So the orange curves are the point estimates, the I get one model that I learned from data. And the blue curves are going to be the Bayesian predictions. And the black curve is the true underlying system with noise. So it's still a noisy measurement, but it's sampled from the true system. Now we see that the orange curves and the blue curves track each other closely, although not precisely. And there are 2 different flavors of each of these curves. The ones with sort of small and close together dots are the 1 step ahead, meaning that we use the black curve the entire time, but when we put the next point down for the orange or blue curves, we use the identified system to put the point down, and then we immediately forget about that point and keep using the black curve. So it only predicts 1 step ahead. whereas the more solid lines, the orange and blue lines, they actually use the learned system throughout the entire trajectory. So it's using its own predictions as its past data to make future predictions. So it's not the teacher forcing a proper trajectory. It is fly by the seat of your pants and hope that your previous predictions were good enough. And here we see on this plot, they were pretty good because we were able to stay with that trajectory pretty tightly. And here is the same plot, but now I have shown the confidence band for the Bayesian model. So this is the 90% confidence band. And we can see that this confidence band does capture a lot of the nominal model shown in dotted black line. And that's a really good thing because if all we had was the blue model, this point estimate, we might not be able to say when we feel like it might be deviating from the actual plant and when our confidence is less in the trajectory. But because the Bayesian model produces this band, it's not something that we had to run multiple times. It produces this band as part of the model. Then using the confidence interval, we are more confident in the position of the true underlying trajectory based on saying it's somewhere within this band, and it might not be on our point estimate at all times. Here is what happens when we attach a controller. So one thing we want to do with especially unstable systems is we want to be able to control them once we have identified them. And for this, we are actually using a single controller. So this is not a Bayesian controller. This is not a probabilistic controller. We are trying to identify one controller which robustly stabilizes as many point models in our posterior system as possible. This is a pretty typical thing that you do in robust control. You assume that you have some nominal plant and then some set of plants within some ball in Hilbert space or whatever set you want to use. And you try to design one controller that can stabilize all of the systems in that set so that if there's some error, you're covered. As long as you don't deviate from your assumed model too much, this controller will stabilize your system. So we're doing this here essentially is the same thing, except that that ball in Hilbert space is replaced with the posterior that we learned from the data in the prior. And for this particular plot, going above a gain of 1 means that we'll grow geometrically forever in the states. And this, where the blue line is, where our posterior band is, having a gain below 1 means that we will geometrically decay to the 0 state. So our system is stable using the controller. And we can see that posterior distribution under this controller is all the 95% confidence interval is all below that gain of 1. So we are fairly confident that this controller will stabilize this system, even though we identified the system with potentially not great data, but because we explicitly said what our posterior distribution is, we are confident that the controller will stabilize it, even though we are not confident of exactly what the system behavior is. And finally, a pitch from our lab. So we take these things in a different direction with the robust control analysis. We are more interested in destabilizing systems and redesigning the system to be less vulnerable to destabilization. So this would be the direction that our lab would take it. We would take that posterior distribution. We would try to design one destabilizing controller to blow up every system in the posterior distribution. And then that would be what we would use our tools for measuring vulnerability, for mitigating that vulnerability by redesigning the system to be more secure. We would extend our work to use this Bayesian posterior. And it's actually fairly simple to make the extension just by using the same tools that we've been using in robust analysis. Only that same idea that instead of using a ball in Hilbert space around a nominal plant, we use the posterior distribution as our set of potential plants. And using that set, because it is informed by the data and the prior itself, is more pertinent to the application because just picking a ball in Hilbert space might not adequately cover all of the uncertainty from the data that you use to identify the system. So the Bayesian system explicitly will say where our uncertainty is in sort of model space. So to wrap up, the bottom line, before trusting the plant that we identify from input-output data, we wanted to put a posterior on a distribution of potential plants, especially in situations where we know that we do not have adequate data to explicitly and precisely identify the system. So having a posterior of potential systems under that data it gives us more confidence in the statements that we make about stability and vulnerability in the systems that we are analyzing. And that is my presentation for Bayesian methods in computer science. Thank you so much. Here are my citations. Thanks.